Have plotted the shear force and bending moment diagram for this overhanged beam for this region, which goes from x is equal to 0 to x is equal to 1.5. In this region, we are successful in plotting the shear force and the bending moment diagram. Now, let's go to the second region of the beam. The second region of the beam goes from x is equal to 1.5 to x is equal to 3, because we are measuring every distance from this free end. So here x is equal to 1.5, here x is equal to 3. So the analysis we are performing now is valid for x is equal to 1.5 to x is equal to 3. So what we have for x going from 1.5 to x going to 3, in this very span, for x equal or greater than 1.5 to x equal to 3, again we will write dv by dx is equal to w. Now in that very region, in the region from x is equal to 1.5 to x is equal to 3, there is no load acting on the beam. Therefore the value of dv by dx, has to be equal to 0. Now see, as we are going to x is equal to 1.5 from this free end, the value of the shear force is minus 60. And we are reaching to point A. At point A, we are having the reaction of the beam, roller support RA, and the value of RA is equal to, from previous equation is 55 kilonewton. So at this very point, we have RA is equal to 55 kilonewton. Now when you are moving from the left hand side of the point A to the right hand side of this point A, we are coming across this value of reaction, which is equal to 55 kilonewton. Now at A, the value of shear force is how much? Minus 60. So as you are moving to the right hand side, you have to add the value of this reaction to the shear force to obtain the shear force on the right hand side. So what we have to do, we know for the region x going from 1.5 to x going to x from 1.5 to x is equal to 3. Again we write dv by dx is equal to 0, because there is no shear force. Therefore v is an isolated constant, and its value will be the value of the shear force on the left hand side of A. The value of shear force on the left hand side of A is minus 60, plus the value of the reaction. The value of the reaction is RA. Since it being positive, it is to be added. So it will be minus 60 plus 55. See, this we have already explained when we have derived the relation between dv by dx and dm by dx for a concentrated load. Because as we are going across a region of concentrated load, as you are moving across a point where concentrated load is acting, the shear force will abruptly change. If the value of shear force on the left hand side of point A is V, the value of shear force on the right hand side of A will be V plus the value of the concentrated load. Okay, so that is minus 60 plus 55. Therefore that comes out equal to how much? Minus 60 plus 55 will come out equal to minus 5. Therefore, as we are going to the right hand side of point A, the value of shear force will be minus 5. Again, write down the equation. dm by dx is equal to V. V is equal to how much? Minus 5. Therefore, dm is equal to minus 5 dx. Now, the value of dm, this is the variable of integration. Let the value of, now see, the value of, now we are integrating from this, we are integrating this equation for x going from 1.5 to x going to 3. Let's suppose we have taken a section here. From here to here, the distance is x. What is the value of bending moment here? Let's suppose the bending moment is m. So we write integral minus 45 to m, because the value of the bending moment, at x is equal to 1.5 is minus 45. So we are writing the value of the bending moment varies from minus 45 to m is equal to integral dx goes from 1.5 to x, because we are essentially in this region. Okay, so at this very point, let's suppose the bending moment value is m. Okay, the value of the bending moment here is equal to m. So how much is the value of x here? 1.5. So the value of the x goes from 1.5 to x, and the value of the bending moment varies from minus 45 to plus m. Okay, so that's what we have done. So integral dm, bending moment varies from minus 45 to m, is equal to minus 5 dx.